Welcome to all of you. Now we discuss paper CC-3 2022 multiple choice question, Calcutta University B.Sc Mathematics Honors. Question paper 2022 paper CC3 second semester under CBCS Mathematics Honors real analysis. Question 1A. Let A equal to semi-closed interval 5, 6 and B is the set of elements 1 plus 1 by n such that n belongs to natural number n. Let S equal to the set x minus y such that x belongs to A and y belongs to B. Then infimum of S is correct option 1, 3. Now, first we discuss some results relating to infimum and supremum. Let A and B be two non-empty bounded sets of real numbers. And this small a equal to supremum of A, small b equal to supremum of B, and let C equal to the set of all those x plus y such that x belongs to A and y belongs to B. Then supremum of C equal to A plus B, that is equal to supremum of A plus supremum of B. And similarly, infimum of C equal to infimum of A plus infimum of B. Now let C equal to is the set of all those elements x type x minus y such that x belongs to A and y belongs to B. Then supremum of C equal to supremum of A plus supremum of minus B is equal to supremum of A minus infimum of B. So this is the important result. Supremum of minus B equal to minus of infimum of B. And infimum of C equal to infimum of A minus infimum of minus B equal to infimum of A minus supremum of B. Note that supremum k into the set A, k is some real number, then equal to k supremum A into A if k supremum of A if k greater than equal to 0, and this equal to k infimum of A if k less than 0. And infimum of Ka is equal to k into infimum A if k greater than equal to 0, and this is equal to k supremum of A if k less than 0. Now come to the given problem, this A set and this B set. So clearly infimum of A equal to 5 and supremum of A equal to 6, and infimum of B equal to 1 and supremum of B equal to 2, because in this type elements this n equal to 1, so 1 plus 1 2, and this 1 plus half 1 plus 1 by 3 and so on. So supremum is of B is 2 and infimum of B equal to 1. Now S is the set of all those x minus types elements x minus y such that x belongs to A and y belongs to B. Then infimum of S equal to infimum of A minus supremum of B, supremum of B. Infimum of A equal to 5, supremum of B equal to 2, so answer is 3. So correct option is 1, 3. Also note that supremum of A is equals to supremum of A minus infimum of B, supremum of A equal to 6 and infimum of B equal to 1, so supremum of S is 5. Next question 1b. Let S is the set of all those elements 1 by n such that n belongs to the natural number n union this set 0 2, and T is the set of infinite union of this open interval 2 minus 1 by n plus 1, comma 3 plus 1 by n. Then S intersection bracket R minus T is correct option is 2 closed. Now S set is this 1 by n type elements. So this 1 by n, so this for n equal to 1, 1. So 1, 1 by 2, 1 by 3, 1 by 4 and so on approaching to 0. So this and this union of these sets 0 and 2. So 0, this S, this 0 is a member of S and 2 is also a member of S. So the limit point of S is 0 and 0, 0 belongs to the set S. So S is a closed set. And T is the set, these type elements infinite union 2 minus 1 by n plus 1, 2 minus 1 when n equal to 1, so 2 minus half, that is 1 and half, and n equal to 1, 3 plus half, that is this. So n equal to 1, so 3 plus 1, 4. So this is the first member, this T1 say, this is the first member up to 4 open interval. And for n equal to 2, this is 1 and 2 by 3 to 3 and half. This is the T2. So union of all these sets is the clearly this is the half, 3 by 2 and 4. This open interval, which is an open set. The union, because we know union of an arbitrary collection of open sets in R is an open set. So this is open set. Now R minus T, R is the set of real numbers, clearly closed set because T is open set. Then S is closed set because the limit point 0 is included in the set S. So this S intersection, this closed set intersection closed set, this is a closed set because the intersection of finite number of closed sets in R is a closed set. So this is a closed set. S intersection R minus T, actually S intersection R minus T, actually this RT 3 by 2 minus 3 by 2 and 4. So this only 2 can be eliminated from this set. So this is this type elements belongs to this and 0 is the limit point of this set. Note that this open set, this arbitrary collection, either finite or infinite collection is always open set. And but arbitrary collection of open sets, we have no conclusion. Arbitrary collection of open sets either may be either open set or closed set. Closed set, arbitrary collection of union, no conclusion can be made here. If closed set, arbitrary collection of intersection, always closed set. Next question. Question C. Let A is the set of all those x, box x, such that 0 less than x less than 100, greatest integer function, are not exceeding x, this, and B is the set 2 to the power I, where I belongs to the set of all integers z. Then A union B is the correct option is 2 enumerable. Now this box x, that means box x means greatest integer function not exceeding x, that is that 0 when 0 less than equal to x less than 1, and box is equal to 1 when 1 less than equal to x less than 2, and box is equal to 99 when 99 less than equal to x less than 100. So this set A contains a finite number of elements, 100 elements, this 0 to 99 integers, 100 integers, this A set, finite number, finite set, this A set. Then is countably finite set. Now B set is 2 to the power I. 2 to the power I belongs to any integer, any integer, so 2 to the power 0, 2 to the power 1, 2 to the power 2, and so on, union 2 to the power minus 1, 2 to the power minus 2, 2 to the power minus 3, and so on. So this is also B is also countable set, but countable infinite or enumerable set. Now the union of a finite set and an enumerable set is an enumerable set. is an enumerable set. So obviously A union B is an enumerable set. Next question, D. 5 to the power n, this is a sequence, 5 to the power n by n factorial plus 3 by 5 whole to the power n. Correct option is 2, converges to 0. First we prove that limit n tends to infinity a to the power n by n factorial equal to 0, where a is a real number and n is a natural number. But for this MCQ, just state this and just give this statement, please. No proof here done here. So this is the proof. If a equal to 0, result is obvious. Take a greater than 0. If xn equal to e to the power n by n factorial, xn plus 1 equal to e to the power n plus 1 by n plus 1 factorial. This is equal to a by n plus 1 into xn. Now, n set of natural numbers is unbounded above, then there exists a m, natural number n, such that 0 less than a by n plus 1 less than 1 for all n greater than m. M is a fixed natural number. Then for n greater than m, we have xn plus 1 is less than xn. Since xn is greater than 0 for all n, so the sequence xn is decreasing and bounded below sequence in R. Let this limit xn equal to k. Then this xn plus 1 equal to qn plus 1 xn. So taking the limits n tends to infinity on both sides. So this xn plus 1 tends to k and this xn also tends to k. So k equal to this 0 into k. Because this n tends to infinity, so q by n plus 1 is tends to 0. So this k equal to 0, n tends to infinity. Hence, limit n tends to infinity a to the power n by n factorial equal to 0 for all a belongs to R. Now, next B for this part. So obviously this 5 to the power n by n factorial tends to 0, and 3 by 5 whole to the power n also tends to 0 because this 3 by 5 less than 1. This is the result. Limit n tends to infinity b to the power n equal to 0 if b modulus of b less than 1 and b not equal to 0. And see 2023 paper CC-3 question 1E, and details proofs as given here there. In the given problem, we get this. So 0 plus 0 is the limit. So the ultimate answer is 0. So correct option is 2. The sequence converges to 0. Question E. Number of subsequential limits of this sequence 1 minus 1 whole to the power 2n sine n by 3 whole divided by n to the power 5. Number of subsequential limit is only 1. Now sine n pi by 3. So pi by 3 actually 60 degree for n equal to 1. So this pi by 3 60 degree. So sine pi by 3 sine 60 root 3 by 2. When n equal to 2, sine 120. See this sine 120 2 pi by 3 sine 120 root 3 by 2. Sine 3 pi by 3, that is pi, is equal to 0. Sine 4 pi by 3, that is this 6 into 4, 240. This minus root 3 by 2. And 5 pi by 3, sine 5 pi by 3, this is equal to 5 into 60, 300 degree. So minus root 3 by 2. And sine 360 degree, that is 6 pi by 3, that is 2 pi, is equal to 0. So this subsequential limit 6n minus 5, when we put n equal to 1, 6 minus 5 is 1. So u1, u7, u period is 6. So u7 and u13. So this subsequence, this u6n minus 5, that is u1, u7, u13, stepping is 6 gaps. So this all this tends to root 3 by 2 for value of sine n pi by 3. Minus 1 to the power 2n is even, this n is always even, twice in always even, so this plus. and this n to the power 5, so 1 to the power 5, 1 by 7 to the power 5, 1 by 13 to the power 5. So this sequence tends to 0. So ultimately this subsequence u6n minus 5 tends to 0 as n tends to infinity. And for this point u6n minus 4, so u6n minus 4 is u2, u8, u14 and so on. And so this for this sine n pi by 3 is root 3 by 2, and this 1 by 2 to the power 5, 1 by 2 to the power 5, 1 by 14 to the power 5, this tends to 0 as n tends to infinity. And sine this 6n minus 3 subsequence u6n minus 3 for this angle 3 pi by 3, so always 0. So u3, u9, u15 and so on, always 0 tends to 0 as n tends to infinity. Next subsequence u6n minus 2, u6n minus 2, this u4, u10, u16 and so on. This value of sine n pi by 3 is this minus root 3 by 2. So this minus root 3 by 2, this 1 by 4 to the power 5, 1 by 10 to the power 5, 1 by 16 to the power 5, this tends to 0 as n tends to infinity. And this for this u6n minus 1 subsequence, u6n minus 1, so this u6 minus u5, u11, u17 and so on. This subsequence, this minus 1 to the power root 3 by 2, this value of sine is minus root 3 by 2, sine this. So this 1 by 5 to the power 5, 1 by 11 to the power 5, 1 by 16 to the power 5 tends to 0 as n tends to infinity. And last subsequence u6n, so u6n is the u6, u12, u18, this subsequence, this all values are 0, so this tends to 0 as n tends to infinity. The number of subsequential limit is only 1. All subsequences even converge to 0. Next question. If let S be a bounded set of real numbers such that S does not have a least element, then correct option is 3. S has at least one limit point. Bounded set of real numbers, S does not have a least element. Let S be a bounded subset of real numbers, and S does not have a real least element. Clearly, bounded set but not least element. So clearly, S is an infinite subset of R. You could consider this 1 by n. This sets 1 by n. So 1, 1 by 2, 1 by 3, 1 by 4, and tends to 0. So 0 is the least element, but this 0 doesn't contain in the set S. So this set 1 by n, 1, 1 by 2, 1 by 3, 1 by 4, and so on, so on. This set S is bounded subset of real number and does not contain the least element. So this clearly this set is infinite subset of R. And because S contains finite number of elements of R, then it has a least element. By Bolzano-Weierstrass theorem, every bounded infinite subset of R has at least one limit point of R. So correct option is 3. This is has at least one limit point. Next question. Question G. Let S be a non-empty subset of R. Which of the following statement is true? Correct option is 3. If X is an isolated point of S, then X belongs to S. So you consider this example, previous example, 1, 1 by 2, 1 by 3, and 0 less than x less than equal to 1. So this bounded set clearly contains infinite number of real numbers and S does not know least point. Next question, this. S be a non-empty subset of R. Let S be a non-empty subset of real numbers R. Now, first option is X is boundary point of S, then X belongs to S. Now, what is boundary point? A point X belongs to R is said to be a boundary point of S if there exists a neighborhood Nx of X such that Nx intersection S not equal to phi and Nx intersection R minus S not equal to phi. And this boundary point X of S may or may not belong to S. Now, this example is the open interval this, then 1, and 2 are two boundary points, but one does not belong to S, 2 does not belong to S. But for this closed interval, 1, 10, these 1 and 10 are boundary points of S, and 1 and 10 belongs to the set S. Next, number 2. So boundary point may or may not belongs to the set S. If X is an limit point of S, then X belongs to S. No. What is limit point? A point L belongs to R is said to be a limit point or accumulation point or a cluster point of S if every neighborhood of L contains a point of S other than L. That is, n dash L intersection S, this deleted delta neighborhood of L, point L, dash means deleted. Delete the point from this neighborhood. Delete the point L from the neighborhood of L. That is NL, neighborhood of L, minus the element L is not equal to phi. The limit point L may or may not belong to the set S. Here, this open interval 1, 2, then the limit points of S, that is this closed interval 1, 2, this limit point 1 is a limit point, but 1 does not belong to this. And 1.5 is a limit point. This 1.5 belongs to the this set S. Next, number 3. If X is an isolated point of S, then X belongs to S. Isolated point. A point X in S is said to be an isolated point of S if X is not a limit point of S. That is, n dash X deleted delta neighborhood of S, X, intersection S equals to phi. Isolated point X of S, of the set S, is an element of S. So, X always belongs to the set S. So, correct option is 3. And last 4, if X is an exterior point of S, then X belongs to S. No, it is wrong because exterior point, a point X belongs to R is said to be an exterior point of the set S if X belongs to R minus S. That is if NX intersection S equal to phi. Clearly, X does not belong to the set S. Next question, 8. The sequence xn is root 1, comma minus root 1, comma root 2, comma minus root 2, comma root 3, comma minus root 3, and dot dot dot. And this Zn equal to 1 by n, this summation of n terms xi for all n belongs to the natural number n. Then this sequence Zn is correct option is 4, convergence sequence. Now first to construct the sequence Zn. This sequence, members of this sequence Zn, first member Z1. So Z1 is the x1 by 1. So x1 is root 1 by 1, that is 1. Z2 is 1 by 2, x1 plus x2. So x1 plus x2 is this root 1 minus root 1, so obviously 0. Z3, 1 by 3, x1 plus x2 plus x3. So obviously x1 plus x2 0. So x3 is root 2. So we take root 2 by 3, Z3. Z4 obviously 0 because x1 plus x2 plus x3 plus x4 equal to 0. Whole divided by 4 is x1 plus x2 plus x3 plus x4 equal to 0. So this even term Z2, Z4, Z twice n always equal to 0. And Z5, this equals to x1 plus x2 plus x5. So divided by 5, this is equal to x5 by 5. This is equal to root 3 by 5. Z5 is this. So this Z twice n, subsequence Z twice n equals to 0, tends to 0, again tends to infinity. But this odd subsequence, this Z twice n minus 1, this is equal to 1, root 2 by 3, root 3 by 5, and so on, dot 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 dot, equal to actually root n by twice n minus 1. Now limit n tends to infinity, root n by twice n minus 1, this is equal to dividing by n on both on numerator and denominator. So 1 by root n whole divided by 2 minus 1 by n. So this n tends to this 0, this 0, this 0, so 0 by some this definite value. So this is equal to 0. So this odd subsequence, this tends to 0, again tends to infinity. Now we have a theorem. The subsequences u twice n and subsequence u twice n minus 1, subsequence of even terms and subsequence of odd terms of a sequence un converge to the same limit L then the sequence un is convergent and sequence un equal to L also. Hence, limit un intends to infinity equal to 0 in the given problem. And the correct option is this convergent, this sequence Zn is convergent and converges to 0. Next question, I. Let A is the set 2 by z plus 1 such that z belongs to this open interval minus 1 to 1. Then AD difference A is correct option is 3, the singleton set 1. AD means the derived set of A, that is the set of all limit points of A minus the set A, minus set A. Now, first we draw this graph. Say y equal to 2 by x plus 1. So if we draw this graph, this y equal to 2 by x plus 1 by Desmos's, then we get this type of this x equal to 1. Here z is equal to actually x, this x z equal to x, say, and this y is the domain set this minus 1 to 1. At this point 1, this value is 1, and this when tends to minus 1, for this lower limit minus 1, this tends to plus infinity. So 2 by z plus 1 tends to infinity. So actually this set A, this is the this 1 infinity, 1 is not included in the set. Actually this z is not equal to 1, so z less than 1, so z plus 1 less than 2. 1 by z plus 1 is greater than 1 by 2, so 2 by z plus 1 greater than 1. So we get this A is the set, this type of interval 1 and 1 to infinity. 1 to infinity is set. Now derived set, that is of A, that is equal to AD. This equals this third bracket 1 comma infinity. Third bracket 1 comma infinity is the closed interval. Actually, is the closed interval. All contains all its limit spawns. So this now AD minus AD difference A, that is equal to AD minus A, that is this closed interval 1 to infinity, this semi-open, this 1 not included, this only singleton set 1. So correct option is 3. Next question, J. If the sequence AN is a monotone increasing sequence of real numbers and bounded above, then the sequence nth term, sum of nth term divided by n, is always convergent. Now, the sequence AN is a monotonic increasing sequence of real numbers and bounded above. It is given that hence the sequence converges to its least upper bound. Let this limit is L, limit intends to infinity n equal to L. Then by Cauchy's first limit theorem, if limit n intends to infinity equal to L, then limit intends to infinity a1 plus a2 plus dot dot plus an whole divided by n equal to L. Actually, this sum can be represented by this summation I equal to 1 to n ai whole divided by n. So this sequence converges to the same limit L, so always convergent by Cauchy's first limit theorem. Thank you for watching this video.